as well as teach us chemistry.
Hello everyone, in this video I'm going to be talking about energetics. Specifically, I'm going to be talking about the types of energy changes and calculations involving energetics. Now, for energy, when you think energy, you think about something that is moving, something that's vibrant, right? Regular day activities. But energy in chemistry and in physics, in the science where we have two main types of energy. We have things being having potential energy, or they have kinetic energy. Potential energy would have been stored energy, while kinetic energy is energy in motion. And of course, you have some other sub energies, some other subcategories such as chemical energy, light energy, heat energy, etc. Now for this topic, we're going to be looking specifically at heat energy, or what we call thermal energy. Right? So, and we look at heat energy. When you hear heat in chemistry, we're really talking about something called enthalpy, right? Enthalpy, or energy change, it can be determined using the measured heat change. So heat change, using our heat change, can help us determine the enthalpy change of a system. And I know this word enthalpy it doesn't sound familiar, but we're going to get into it a bit shortly. Right? So enthalpy change, it's the measured heat change of a system, right? And it cannot be measured directly. So we cannot measure it. We cannot just say, okay, we're gonna get up and measure the enthalpy change right now. That's just not how it happens. We have to first take what we call the temperature change. And as we know, temperature change is something that we can actually measure. We can use a thermometer to measure the temperature change, right? Now we have two main types of energy changes. We have what we call the exothermic and the endothermic reactions that involve energy. Now for exothermic reactions, these reactions, they release heat energy. So for exothermic reactions, these reactions, as it says, they release energy to the environment. And you hear me talking about environment, so let me just explain a little briefly on what system and environment is. So here I have my container. Right, so this is my container here. Right, this is what we call the system. Everything inside this container is the system, and I put a lid over the container. Everything outside this container is what we call the environment. So this is the environment, and this is important. So this is the environment, this is the system. Right, so the system is everything inside the container, the environment is everything outside. Right, now for exothermic reactions, let's say we had a reaction occurring, the reaction occurred, and some form of heat is evolved to the environment, so the environment feels warm. That's an exothermic reaction. It releases heat energy to the environment from the system, and as a result, because heat is being lost, we have a negative enthalpy change. Right, because heat is being lost, the enthalpy change is negative. And we're going to look at how our exothermic reactions look. Right, now as I said earlier, for exothermic reactions, we would have lost energy, and initially we're starting off with our reactants. Remember, for a reaction, it starts from reactants goes to products, and in order for a reaction to occur, some form of energy must be involved. So we absorb energy. Oftentimes we absorb energy to break bonds, and we release energy when new bonds are formed. So we form new bonds, we release energy, right? And this occurs for all reactions, right? We absorb energy to break the reactant molecule. So if we had a reaction A, B plus C, D, would absorb energy to break these apart and to form something new, such as A, D plus BC. To form something new, energy would have been lost. Right, now for our exothermic reactions, remember, energy is being released. So what's going to happen is that, let's say we start off with our reactants, and the products themselves would have less energy because energy would have been lost. So I'm going to start off here for my reactants. This line is my reactants, Remember, exothermic, we release energy to the environment. So the reactants would have started off with a high energy. And when the products are formed, these products, since energy was lost, the products have a low energy. So the line would be down here. So up at the top representing higher energy and lower would be low energy. Okay. All right, remember that energy is lost. That's why the products have a lower energy than the reactants. Okay. Now, for this type of diagram, you have to show the activation energy, right? And the activation energy, this is the minimum amount of energy needed to break the bonds in reactants. That's our activation energy. So minimum amount of energy. In order for the reaction to occur, our reactants would have had to gain this minimum energy so that they can react, right? And it's almost like a hill, you know, like when you're pushing something up a hill, right? You push it up the hill, you have to gain all of that energy in order for you to cross the hill and go over. Note the connection that I'm making, and it goes to the products, right? So note that the activation energy goes from the reactants to the top of the hill, because remember, it's the reactants that need to gain that energy, not the products. The reactants need to gain enough energy to break their bond. So this would represent my activation energy, EA. That's activation energy. And we need to also put in our enthalpy. Now note that the energy is being lost, right? And it's being lost from our reactants to our products. It is being lost from our reactants to our products. So this is where the reactants started to the products. So between here to here is going to be our enthalpy change. Enthalpy change is represented with the symbol triangle H. That's enthalpy change or heat change, right? And note that this is negative for exothermic reactions, and that's our diagram there. Now looking to endothermic reactions, these reactions, they absorb energy, right? So they're going to absorb energy from the environment, and the system is going to get that energy. So it goes from the environment to the system, it gets that energy, and once it gets that energy, the environment, so it took all the energy from the environment. So what's going to happen is that the environment is going to feel cold. The environment no longer has that warmth, so it's going to feel cold. So hence we say that for endothermic reactions, energy is being absorbed and it feels cold. And since energy is absorbed, we're gaining energy. It's going to be a positive enthalpy change, a positive H plus, right? Now for the diagram, it's very simple. You just have to think about what's really happening. So for endothermic, remember again, we're absorbing energy. So initially our reactants would start off low, and since we're absorbing energy, the products that are formed are going to have a higher energy, right? So we absorb energy for our products to form, so the products are going to have a higher energy, right? And once again, we do need an activation energy for those reactants to react. So the reactants have to jump over that energy barrier in order for them to break, to form new molecules or new compounds. Now once again, for activation energy, it goes from the reactant to the top of our hill. So I'm drawing a line. I know it's not straight, but it should be a straight line. Drawing a line from the reactants to the hill. That's going to be my EA, which is activation energy. And the change in enthalpy is going to be between the reactants and products, and that is positive since you would have gained energy. So just remember that exothermic reactions, they release heat to the environment. The enthalpy change is negative and they feel warm. And since they release heat to the environment, the products would have had a less energy compared to the reactants. While for endothermic reactions, these reactions absorb energy and they feel cold. The environment feels cold because we would have absorbed energy, and so the enthalpy change is positive. Since we would have absorbed energy, the products that we form would have had a higher energy compared to the initial reactants that we had. And another recap is that activation energy is the minimum amount of energy that we need to break the bonds in reactants. Okay, so catalysts, these are substances that lower the activation energy without being used up themselves or without being used up in the chemical reaction. And the catalyst does in fact affect both the exothermic and the endothermic activation energies. Remember, the catalyst, it lowers the activation energy. So it just creates an alternate pathway for the reaction to occur. So what's going to happen? It lowers activation energy and it's going to come down and we will form the same amount of products. So this activation energy would be the activation energy without the catalyst. So this is without the catalyst. And this is the activation energy with the catalyst. On the other hand, for endothermic reaction, once again, the catalyst finds or provides an alternate pathway for the reaction to occur by lowering the activation energy. So it's going to come from the reactants. It's not going to go to the top. It lowers activation energy and we form the same amount of products. Alright, so I'm just going to label this. This is my activation energy without catalyst. And this is my activation energy with the catalyst. Alright, and this is very important, especially when you're doing rates of reactions. It's very important. Okay, so now we're going to look at calculations that involve the heat of neutralization versus the heat of solution. And we just need to recall enthalpy change, or enthalpy change rather, we cannot measure it directly. And so we have to use the temperature change of the system. Right? And for temperature change, you have to note this, that the temperature change is the change in temperature of the environment. So we do in fact measure the temperature of the environment. So let's say something feels warm, the temperature is going to increase and the thermometer will have a rise in the bulb. So we're going to see an increase in the mercury in the thermometer. Right? So if the temperature increases, we're going to see a rise in the temperature in the thermometer. However, once the environment would have felt warm, once the environment would have gained that energy, note that the system itself would have lost the energy. So the system, it feels cold. Or inside the system, we cannot feel it, but the molecules themselves are cold. So while the molecules are cold, the environment is warm. And that's for exothermic reactions. Right? So exothermic reactions, you expect an increase in temperature and a negative enthalpy. While for endothermic reactions, the environment is going to decrease in temperature. It's going to feel warm. It's going to feel cold. While the environment is going to decrease in temperature. It's going to feel cold. Right? It's going to feel cold. And remember that we're absorbing energy from the environment. So the system itself gains that energy and it feels warm. So the molecules itself would feel warm while the environment that we're measuring the temperature for. So even though we put the thermometer in the system, right, it's actually measuring the temperature for the environment. So the environment itself will feel cold, right? So note that endothermic reactions, their temperature decrease, the environment gets cold while the enthalpy is positive. Now note the following as well, the difference between heat and temperature. So heat is the transfer of thermal energy. Remember that we cannot measure this directly. It's the transfer of thermal energy from one body to another. While temperature is the measure of how hot or how cold something feels, how it feels based on the movement of particles within it, right? So if the particles are moving very fast, they would have a high kinetic energy and a high temperature. If the particles are moving very slow, they would have a low kinetic energy and a low temperature. Alright, now for our calculations, there are a couple of things that you need to note. For one, the specific heat capacity of water, which is which we use as small c as the symbol. The specific heat capacity of water is 4.2 joules, J for joules, G for grams, and this is degrees Celsius. Now, the specific heat capacity of a substance means the quantity of heat required to change the temperature of a unit mass by 1 degrees Celsius or 1 degrees Kelvin. And why it is by 1 degree Celsius or 1 degrees Kelvin is because if the temperature change in Celsius is 3 degrees Celsius, it's going to be 3 degrees Kelvin or 3 Kelvin, right? So the temperature change remains the same whether you're in Kelvin or Celsius. Now, for specific heat capacity, as it says, it's the heat required to change the temperature of a unit mass, of a particular mass, by 1 degree Celsius. And so as it relates to the specific heat capacity of water, it says that 4.2 joules per grams per degree Celsius is required to change the temperature of 1 grams of water by 1 degree Celsius, right? So you just need to know this value, 4.2 joules per grams per degree Celsius, for the specific heat capacity of water. Then we have the temperature change, and for temperature change we use the final temperature minus the initial temperature, and it's oftentimes represented using degrees Celsius. For density of water is equal to 1 grams per centimeter cube, and it uses for all substances, whether it's hydrochloric acid, sulfuric acid, sodium hydroxide. So you're going to use this density for each of them, 1 gram per centimeters cube. And let me just put my slash here. Right now, what this is saying is that 1 gram is equal to 1 centimeters cube. Therefore, 40 grams is equal to 40 centimeters cube, or 50 grams is equal to 50 centimeters cube, and vice versa. Right now, heat in our system, heat can be gained or lost since the system is not in a vacuum. And if the system were in a vacuum, it prevents heat from escaping or heat from entering. But since it's not in a vacuum, even though it's a closed system, heat can actually in fact enter that system or be lost. So we have to keep that in mind. However, we can use what we call a calorimeter, which is an insulated container. Remember, insulated means that it does not absorb heat, right? So this container, it's an insulated container that prevents heat from being absorbed or released, right? For example, polystyrene cups, and we use these a lot in the lab. So we use a polystyrene cup, and you use it even if you're drinking. You use it, right? If you have soup, you put your soup in that cup, and it prevents you from getting burned by the hot soup, right? So that's our polystyrene cup. It prevents heat from entering or from being released into the environment. Right now, for our calculations, we have two types of calculations that we're going to look at for energy changes. We have heat of neutralization and heat of solution. So for heat of neutralization, as it says, neutralize, when you think of the word neutralize, you're thinking about acids and bases, right? So the heat of neutralization is the heat change when 1 mole of water, because remember, neutralization, you react acid and base to form salt and water. So it would be the heat change that we get when 1 mole of water is produced between the reaction of an acid and an alkali. So it's a heat change when 1 mole of water is produced between the reaction of an acid and an alkali. And this is just an example here. We have our HCl and our NaOH, the acid and the base, reacting to form the salt and the water. And of course, some form of heat would have been evolved. Now this water, the 1 mole of water that we produce, is very important. We're going to use it in the calculations, right? The 1 mole of water. Okay, also whenever we're doing the temperature change, we have to first find out the initial temperature, right? So let's say the initial temperature of the HCl was 29 degrees Celsius and the initial temperature of NaOH was 27 degrees Celsius. And you think, but these two substances have their own initial temperature. So when you're calculating the temperature change, which is F minus I, final minus initial temperature, you have to calculate the initial temperature of both of our substances, both the acid and the base. So if we were to average this, 29 plus 27 divided by 2, that gives us 28. So our initial temperature would have been 28 degrees Celsius. And let's say the temperature of our solution, our salt solution, would be 36 degrees Celsius, and we put our thermometer in there. So our final temperature is going to be 36 degrees Celsius. And therefore, the overall temperature change is equal to 8 degrees Celsius. And that's how we calculate the temperature change. Remember that you have to average the initial temperature of the both of the substances, and then you plug it into the final minus initial temperature calculation. Now to calculate heat of neutralization, it's very simple. You just need to remember this formula. So heat of neutralization is equal to Q over -1. Note that it's a common Q divided by -1 times mole. Now to calculate Q, Q is equal to MCAT. You've heard this before somewhere. Q is equal to MCAT. M being the mass of the solution being these, the HCl and the NaOH combined. So if HCl was 50 centimeters cube and NaOH was also 50 centimeters cube, the overall volume of the solution is going to be 100 centimeters cube, and therefore the mass is 100 grams based on the density of water. Remember that density is 1 gram is equal to 1 centimeters cube. That's why I said that 50 plus 50 gave us 100 for the volume, and the mass would be equal to 100 grams, right? So that would be the mass of our solution. Then we have C. Remember, common C means specific heat capacity, which is 4.2 joules per gram per degree Celsius. And of course, I would have shown you how to calculate the change in temperature already. And that's for heat of neutralization. For heat of solution, you think of solution, you think about two different substances. You think about a solute being dissolved in a solvent, right? So solute being the substances being dissolved, right? And the solvent being the substance doing the dissolving. So in the case of salt and water, salt would be your solute. Salt being the solute, it's gonna get dissolved in the water, which is the solvent, right? So we say that the heat of the solution is the heat change when 1 mole, I should have highlighted this, when 1 mole of a solute, so the solute we're looking at this time, when 1 mole of a solute dissolves in a solvent, right? So the heat change when 1 mole of a solute dissolves in a solvent. Just remember, the heat change when 1 mole of a solute dissolves in a solvent. And if we were to have further dilution, right? If we were to have further dilution, if we were to add more things than the solvent could hold, then there would actually be no further dilution. So if we were to add more things to the solvent than the solvent can actually hold, there would be no further dilution and no further heat change, right? So even if dilution does occur, right? So let's say we had a temperature change up to 30 degrees Celsius after we added our salt. So we added our salt, particular salt could be copper sulfate, to water, and we saw a temperature change. And we just paused for a minute. And after some while, we decided to add more copper sulfate, right? You won't see another change in temperature because all of those copper sulfate molecules would have actually reacted already, and so no further change in temperature would be seen. Now for heat of solution, now for heat of solution is calculated using the same formula. Heat of solution is equal to Q over -1 times mole. However, the values are a little different. So Q is equal to M cat, but M being the mass, it would be the mass of the solvent. So we're going to convert, if we got the solvent to be 100 centimeters cube, therefore its mass is going to be 100 grams, right? So it's going to be the mass of the solvent times specific heat capacity, same specific heat capacity, times the temperature change, right? Which is final minus initial temperature. Now the moles is going to be the mole of the solute. Remember that the solute is being dissolved in the solvent. It says the heat change when 1 mole of a solute is dissolved in the solvent. So the mole is going to be the mole of the solute, right? Okay, now join me in my next video as I go through some calculations involving heat of neutralization and heat of solution. Alright, so that's it for this video. Join me in my next one where I will be doing some calculations on heat of neutralization and heat of solution. Thanks for watching. That's it with Miss Wallace Teaches Chemistry.
Miss Wallace teaches chemistry.